Okay, so hi Dr. Chen. So this is my presentation about nuclear magnetic resonance. So my name is Muhammad Nur Adli. My metric number is 193979. Okay, let's proceed. So I would like to start with the meaning of the nuclear magnetic resonance itself. So it is actually a physical phenomenon in which the nuclei in a strong constant magnetic field are disturbed or perturbed by a weak oscillating magnetic field in the near field of it. So it responds by producing an electromagnetic signal with a frequency characteristic of the magnetic field at the nucleus. Okay, so actually the process is occurred near to the resonance effect when the oscillation frequency matches the intrinsic frequency of the nuclei. So it is actually depends on the strength of the static magnetic field, the chemical environment of the magnetic field, and also the magnetic properties of the isotope involved in this experiment or situation. So, okay, this is one of the practical application, but actually we will discuss it further next. Okay. So actually, this is overall or the imagination. No, no. Actually, this is the history of the nuclear magnetic resonance. So it is start during at the years 1937 by Rabi. So he predicts then observed that the nuclear magnetic resonance. Of course, it was uh, for the experiment by Bloch and Puzzle, which first nuclear magnetic resonance of Bob sample. So also he wins the Nobel Prizes at the 1946. So this one next is Oberhauser, which invent the nuclear Oberhauser effect, and then Ernst Anderson, which produced the Fourier transform of the nuclear magnetic resonance, and then in 1975, Gina and Ernst producing the two-dimensional of nuclear magnetic resonance visualization. So next is yes, still Earth's history here. So the Woodridge in 1985, which find the first solution structure of small protein from the NOE. So NOE actually is before uh, Overhauser nuclear Overhauser effect from distance restraint. And then we proceed at 1987, which is we have invent the three-dimensional nuclear magnetic resonance is start to develop by the carbon and nitrogen isotope labeling of recombinant proteins resolution. So in 1990, the pulse field gradient it is actually an artifact suppression. In 1997, the residual dipolar couplings RDC from partial alignment in liquid crystalline media, molecular weight more than 100 kDa. And then in 2000, the dynamic nuclear polarizations is produced to enhance the nuclear magnetic resonance sensitivity, which leads to our application until today. Okay, so I would like to share about the principle of the nuclear magnetic resonance. So actually, it involves three sequential steps here. So the first one is the alignment of the polarization of the magnetic nuclear spins in an applied constant magnetic field, which is denoted as B naught. And then the perturbation of this alignment of the nuclear spins by a weak oscillating magnetic field, usually referred to as a radio frequency pulse. The oscillation frequency required for significant perturbation is dependent upon the static magnetic field B naught and the nuclei of observation. And the last one is the detection of the nuclear magnetic resonance signal during or after the radio frequency pulse. It is actually due to the voltage induced in a detection coil by precession of the nuclear spins around the magnetic field, the constant magnetic field before. So actually after the radio frequency pulse, the precession usually occurs with the nucleus intrinsic Larmor frequency and in itself does not involve transition between spin state or energy levels. So actually what is Larmor precision here? Meaning uh, uh, Larmor frequency here. So Larmor frequency or later we call Larmor precision is about the magnetic moment of an object about an external magnetic field. So I think later we'll discuss more. So basically, the nuclear magnetic resonance, the most basic one is about the electromagnet. So these are about the two figures in the magnet area, which is Faraday's law and Lenz's law, uh, which is not will be discussed further here. But actually, this is one of the fundamental of the nuclear magnetic resonance. So this is the direct application of the nuclear magnetic resonance. From previously, we discussed about the meaning of the nuclear magnetic resonance, which they are static kind of the magnetic field, which perturbed by the near magnetic field. So actually, we can see it here. So it is quite related with the Lenz law and as well as the Faraday's law before. So from here we can see that a moving perpendicular external magnetic field will induce an electric current in a closed loop. So the magnetic here is upward, and in the middle of the nuclei there are magnetic field produced by a circulating electron. So an electric current in a closed loop will create a perpendicular magnetic field, which will cause to the nuclear magnetic resonance as well. So it's all about the magnet here. So in nuclear magnetic resonance also there are a lot talking about the quantum mechanics. So one of it we cannot run from the spin's orientation in a magnetic field, which is in energy levels study of the nuclear magnetic resonance. So actually the magnetic moment are no longer equivalent. The magnetic moments are oriented into I plus 1 direction in magnetic field. So it is actually the spin number of the magnet. So the vector length of the angle is given by the vector length is given by h bar I Z I plus 1. The angle is given by cos Z m over I plus 1. So the energy is given here negative m mu over I b naught. So from the picture here, we can see that the magnetic level of the nuclear magnetic resonance here, uh, which is described by the equations in the left here. So these are the example of the difference in energy between the two states of these two states, which is the delta E is given to gamma H B naught over 2 pi. So the B is the external magnetic field, the H is Planck constant, and the gamma is zero magnetic ratio. So actually, I think I'm not putting the zero magnetic ratio discussed here, but actually zero magnetic ratio is very important in the nuclear magnetic resonance because it is part of it and it will give an effect to the so that the nuclear magnetic resonance is happen. So from the quantum description, so actually the nuclear magnetic resonance, nuclear spin, uh, the nuclear rotates about its axis, the I value. The nuclear with spin have angular momentum or spin total magnitude h bar set I plus 1, which is it is a quantized. So 2I plus 1 actually state that the spin number of the nuclear magnetic resonance is a half, as we previously look at the figure before. I is equal to half. So the identical energies in absence of external magnetic field. So the theory of the nuclear magnetic resonance in classical description is this. It is depends on the how the nucleus will get around towards an orbit around an applied magnetic field. Yes, precessional orbit here. So it is quite related to the gyroscope, gyromagnetic ratio previously. So is talking here about all the formula cos equal to Zm over I plus 1. And then it's proceed with the formula, which is angular velocity of the motion is given by omega naught equal to gamma v naught, because it is always in a circular motion of the spinning nucleus, where the frequency of precession or Larmor frequency is equal to v equal to gamma b naught over 2 pi. So it is actually equivalent to the what quantum mechanical description before from the classical description angle. Okay, so this is the net magnetization. The nuclei either align with or against external magnetic field along the z-axis. Since mononuclei align the field, net magnetization m0 and mz axis parallel to external magnetic field. So this is uh, what we can see from the meaning before. So in the figure here, it shows that the net magnetization along the positive z, since higher population aligned to B naught. So magnetization in x and y plane averagely is 0 because it follow from what the net magnetization value. So we have a net magnetization precisely about the magnetic field at a frequency of omega naught with a net population difference between aligned and unaligned spins. So this is actually shows that the spin population is perturbed or is disturbed, or this is language that I easily understand, and perform spin gymnastics. So this is the basically imagination of what is an nuclear magnetic resonance experiments principle. Okay, still more. So this is the theory of the nuclear magnetic resonance description. Actually, this is the comparison between the classical angle, with the quantum description, which has been discussed before. So actually, from the classical view, we can obtain the formula of the angle, and from the quantum description, we can obtain the energy difference formula, and also its description about the quantum spin number. So this is the nuclear magnetic resonance spectroscopy, which is one of the application of the nuclear magnetic resonance. So what is all about? So actually, it is most commonly known as nuclear magnetic resonance spectroscopy. It is a spectroscopic technique to observe local magnetic field around atomic nuclei. The sample is placed in a magnetic field, and the NMR signals is produced by excitation of the nuclear sample with radio wave into nuclear magnetic resonance, which is detected with sensitive radio receiver. So at the left side, we can see the picture of the nuclear magnetic resonance spectroscopy. So actually, the intramolecular magnetic field around an atom in a molecule changes the resonance frequency, which giving access to detail of the electronic structure of molecule and its individual functional group. So actually, has been used to identify the monomolecular organic compound, and also to identify protein, complex molecule, and it will give us the detailed information about the structure, dynamics, reaction state, and chemical environment of molecule. So it is very important and nice. So the next one is the relaxation of nuclear magnetic resonance. So this is quite hard to explain actually, but let's try. Okay, so actually there are two kind of relaxation of the nuclear magnetic resonance. So the first one is spin lattice, or we call it as longitudinal relaxation. So actually it's transfer of energy to the lattice of or solvent material. So the next is the coupling of nuclei magnetic field with magnetic field created by the ensemble of vibrational and rotational motion of the lattice or solvent. And the last one is the results in a minimal temperature increase in sample. So this is the visualization of the longitudinal relaxation. So the cycle delay here stated that the general practice is to wait 5 times spin lattice for the system to have fully relaxed. And the next one you have T2 also, so which is kind of spin, or we call it as transverse relaxation. So this is the exchange of the energy between the excited nucleus and low energy state nucleus. Also, to randomization of spins or magnetic moment in XY plane. So yes, this is a picture of the phasing of the spin of the X and Y axis. Okay, lastly, so this is the application of the nuclear magnetic resonance overall. So it can be used to obtain what I have mentioned before about the structure of detail. So here stated structural chemical elucidation. So it can see the natural product chemistry, synthetic organic chemistry, which analytical tool of choice of synthetic chemists is also used in conjunction uh, with MS and IR. Uh, the drug design, yes, we can study about the structure activity relationship by nuclear magnetic resonance. Study of dynamic process. So actually the reaction kinetics, study of equilibrium of the chemical or structure of protein, of nuclear, and so on. Or also to study the structure of 3D in 3D as protein ligand complexes, DNA, polysaccharide. Actually, in the field, they are commonly used by the medicine by the doctor, which to scan the human brain. So this is the example of the MRI images of the human brain here. So I think that's all for my presentation. I am very sorry, doctor, if I cannot explain it with very detail, with very good and nice. And also, I think there are some of the miss part of it. But however, thank you, doctor, for giving us um, for, to present the presentations here, even with an online situation. Thank you, doctor. Thank you very much for this semester, for all the journey here. So thank you so much. Bye, doctor.